All right, team, here we go. Chapter 11, lesson 3-1. This is our last lesson in chapter 11, last lesson in CCA2. You're almost there. So, we're going to take a look at when is probability counterintuitive, meaning that, like, hey, if we see something that we've got a probability and you just look at it at face value, like, oh, that's clearly going to be like this. We should probably do that because the odds of it are just so good. But then we actually do them. You're like, oh, wait a second. Actually, I might feel differently now. So we'll look at 3 different situations and go from there. Okay, so Shifty Shauna. So basically how this is going to work, there'll be 3 problems. We'll start kind of small. We'll build up to some bigger numbers. And our last problem will have some pretty large numbers to it, but it's all kind of the same process here. So it says this, Shauna has a bad relationship with the truth. She doesn't usually tell it. In fact, whenever Shauna is asked a question, she rolls a dice. If it comes up 6, she tells the truth. Otherwise, she lies. So if Shauna flips a fair coin, so 50-50, and you ask her how it came out, what is the probability she will say heads and is telling the truth? Use an area model to solve this problem and carefully record your work. Be ready to share your solution here. So we're going to use an area model here. And specifically, I'm going to divide this into 4 boxes because I got multiple things that are happening here. One, she's rolling a dice. So 5 out of 6 times she lies, and 1 out of 6 times she tells the truth. So this is if she rolls a 6, and then if she rolls anything else. Then we've got our fair coin. So we've got a half that it's heads, and we've got a half that it's tails. So let's get some of these numbers going in this box here. So 5, 6 times by 1/2. So I'd end up with 5 over 12. 1/2 times by 5, 6. Again, I've got 5 over 12. Truth, well, I've got 1/2 times by 1/6. I'm going to have 1/12, and I'm going to have 1/12, and then just confirm that everything works. 6 out of 12, 6 out of 12. That makes a total of 12 out of 12 or 1. So we're good. So everything is going to work out here. If you want to see it this way, you can also see it this way. Everything seems to line up and make sense there. So the question says this. What is probably she says heads and is telling the truth? So she needs to say heads and tell the truth. Okay, well, it's what's this box right here? So we're thinking that that is a 1/12 possibility there for saying heads and telling the truth. Let's take a look at our next question here. It's going to be question B. It says this. Suppose Shauna flips a fair coin. You ask her whether it came up heads or tails. What is the probability she says heads? So there's a couple of possibilities here. One, it comes up heads and she tells the truth. Okay, so there's one piece of it. Two, it comes up tails but she lies because then she lies and she'd say heads. So I've got 1/2, or excuse me, 1/12 that it comes up heads and she tells the truth. Here she would say heads because it comes up tails, so she needs to lie. So I'd have 1/12 plus 5/12. I would come up with half the time. She would say that it would be heads and doesn't matter if it's right or wrong because that's just what we have there. So that is that. So we have 1/2 there for our second question. Okay, so this is the basic idea. Now we're just going to start to grow some of these numbers and not make them quite so easy, like a 6 and a half and things like that. Let's take a look at question 85. Which, let me tack on one thing to this. This is that kind of thing there where we go, okay, if she lies 5/6 of the time, it feels like we're not going to get this same 50-50. But look at that, we end up with that same 50-50 of heads and tails, even though she's lying most of the time. So that's kind of that connection back to the start of the lesson, which was when is probability counterintuitive? When is it counterintuitive? Okay, now let's move on to question 85. Okay, team problem number 85 here, and this is going to be a twist on some Harry Potter stuff. So if you want to read this, you sure can, but of course, due to copyright, they don't actually say all of the correct names. But here's the key thing: there are 5 people at the school who have red hair out of the 100 students. And this groundkeeper says that she saw a kid with red hair doing this. But it was dark, so they had her go and do a checklist. And 4 out of every 5 times uh she correctly predicted that a student had red hair or not. So what that means to you is that most of the time, 4 out of 5, 80%, she is predicting the right hair color, and there's only 5 out of 100 students that have red hair. or I should say, this is not just the right hair color. This is 80% of the time she predicts red or not correctly, and 5 out of the 100 have red hair. Those seem like pretty convincing elements that probably one of those kids did it. But let's see what the actual math on this says. So we're going to make a probability model for this. Again, we're going to do it with our area diagram and go from there. So we have, so this is red hair. Let's see here. I'm actually going to make this be a little bit different here. So we're going to go red hair up here. Well, that's 5 out of 100. And then I'm going to go with not red hair. That's going to be 95 out of 100. Okay. Then on the groundskeeper's report, we're going to say that 4 out of 5 times she's correct. And then she's not 1 out of 5 times. Okay. Now I'm just going to fill in these values in the table here. Okay, so there are our values here. Thief is not correct, or thief is not that, and then Lily's hair color prediction is this. Let's take a look at this table on to the next questions on the next page. Okay, so here's our chart, and then moving on B. If you perform the experiment with 100 students, how many times would you expect Lily to say the student had red hair and be correct about it? Well, here's red hair, and here is correct. I would expect her to say that she's got 4 students that are correct. That's that 4%, or 4 out of 100 that she is getting right there. Okay. So now all this other stuff, these are just all the names that I skipped over here. La, la, la. So here's what I want to say. If you perform this experiment with 100 students, how many times would you expect Lily to say the student had red hair? Okay. Well, had red hair, we know for sure it's this one, because she would say that they had red hair and were correct about it. But then we'd also say this. So they do not have red hair, but she's not correct about it. So actually here we have, so which parts of the diagram, we would have these two. So how many times would you expect Lily to say the student had red hair? We'd expect her to say it 23 times. Which now, when you look at it and go, oh, wait, and she's only right for those, you can kind of see where we are going with this. So let's see what the next question says. Okay, so I'm actually just going to add these questions in here because I don't have to put all this stuff back on the next page here. So let's slide down. It says this: if you perform this experiment with 100 students, what percentage of the students Lily said had red hair would actually have red hair? Well, that would be 4 out of the 23 times that she would say that. So 4 out of 23 ends up being kind of a crazy decimal. So we'll just round it off. We'll call it about 17.39% if you want to get real exact, but rounding it off, like I said, let's just call that 17% of time. So 17% of time, she actually is right about a student who has red hair and is actually the person. So that is pretty interesting there now, because before we said, hey, 80% of the time she is getting it right, and there's only 5 kids that have red hair, but that translates down to 17% of the time she's actually right about them having red hair, which is kind of interesting. So can you use these calculations to defend your friend? Is it likely that Measley was the thief? Yes, you can definitely use these to defend your friend, because you can say that, hey, only 17% of the time is she correct. Is it likely that Measley was the thief? This is more of a can't tell type thing, because we're assuming that every student has equal chance to like be that, it's all kind of random numbers, but obviously there are some students that are going to be more likely to do something than some other like students, so you can kind of weigh out like a bunch of those things and do some things like that. And so there, you actually couldn't like perfectly prove this. So no, you can't actually like perfectly prove this, is because there are some other factors. It's not just a straight probability roll, because these are humans, and humans are never just a straight probability roll. All right, let's go to our very last question. This question number 86, and that's going to have the biggest numbers in it, but it'll be the same type of process here. Okay, so in this problem, we're going to talk about testing for AIDS. In this part of the paragraph, they just basically talk a lot about some of the more difficult reasons that you might want to test or not test people for AIDS, and what are reasons for that, or I should say AIDS slash HIV. And so I'm going to skip reading that just because it's kind of crazy. And you guys are readers, you can figure it out. But here are our key numbers here. So in order to explore these. Suppose that the current HIV test is 99% accurate, and that suppose the population to be tested 100 out of 100,000 people actually are HIV positive. The question is, what is the probability that a healthcare pra- practitioner, so these 100 out of 100,000 people, would be identified as having the AIDS virus who actually did not? So that's kind of our key topic here. So one last thing here, this is a case where again it seems pretty convincing. Like, hey, if a test is 99% accurate, we should probably be trusting this test to see kind of what happens. But let's see what happens when we actually do the probabilities here. All right, team. So it says make a model for this situation. So I've got sick and not sick. I've got correct and not correct. Remember, the test is 99% accurate. So we're going to just call this as, let's not put decimal there, 0.99. Not correct would be 0.01. Sick, there was 100 people that were sick, which means that out of that 100,000, that 99,900 would not be sick. Okay, so that's the start of our model. Let's get some of these boxes filled in here. So that means that 99 of the 100 that are sick would be predicted accurate. One of them would be predicted would be told that they were not sick when they actually were sick. And then of our people that were not sick, 98,901 would be predicted correct, which looks pretty good right now until you get down to this box. 999 would be told that they were sick when they're actually not sick. Oh, like all of a sudden you can see kind of where this problem is going here. So it says this, how does the number of people who are HIV positive compare with the number of people who will be told they are HIV positive? So the number of people who actually are HIV positive, we got 99, compare with the number of people who will be told they are HIV positive. So jumping back to our question, it says this: how does the number of people who are HIV positive compare with the number of people who are told that they're positive but are really not? Well, that's really different. You've got 99 who are HIV, or excuse me, you've got 1,098 who are told that they are HIV positive, but are really not. That's 999. Like, there's just quite a difference there between those that, like, oh man, like you're telling almost 1,000 people that something's really terrible when it's really not. Next up, if a randomly tested health practitioner's test comes back positive, what is the probability he's actually not HIV positive? So not HIV, well, that would be here divided by our 1,098. That's actually about a 91% clip. It's 90.98. So about 91%. So about 91% of this 99% accurate test will come back as false positives, which is pretty crazy to think about. All right, team. So let's keep going down to these other questions here. So it says, write up your statistical conclusions about the mandatory testing of health practitioners. How might your statistics change if the study was about subjects in the general population who volunteered for testing? So basically, what this says is that, hey, if we're going to get this 91% wrong, we probably shouldn't be doing a whole population, we should not be doing a whole population um, vote there, just because that's going to create so many other uh, people that are tested that don't really need to like have a test or think that they should, and then you're going to be telling some people some pretty devastating news when it's not actually true. But how might this change? Well, if you're only doing the people who are volunteering, you're just going to end up with a lot less people, just a ton less. So instead of testing 100,000 people at 99% accuracy, you might only be testing 1,000 people. And because maybe there's only 1,000 people that have reason to believe that something might have happened, or that or that's something like that, well then in that case, now at 99% accuracy, you're only telling 10 people that it's wrong, which that still is is really terrible and sucks for those 10 people, but that's and it's not actually 10, it is 9 people. But that's way different than 999. Like 1,000 people is just way different than 9 people. And so that's why even when you hear that something is 99% correct, when you start to deal in big numbers, you have to think about what are the long-term ramifications of that 1% that is wrong or that is inaccurate. So moving down to your last question, question E in the last section before you get into review and preview and closure, of course, but last lesson question here. It says, are the test results mathematically independent of the fact that a person tested does or does not have AIDS? Okay, mathematically independent. Let's think back to chapter 10 of CCG. For something to be independent, two events are independent when the outcome of one does not influence the outcome of the other. So let me say that again. Does the outcome of one, so the HIV test, does that is that not influenced by basically the people being tested? Well, absolutely, that's true. This is still going to be 99% accurate if you test 100,000 people or if you're testing 100 people. Like just this is always going to stay independent. It's always going to stay at 99% accuracy. So, um, uh, and not just based on the quantity of people. It's I should say it's not impacted whether a person is sick or is not sick. That doesn't matter to the test. That is not changing its value there or its accuracy. It is an independent event. There we go. Review and preview in your last section. That's it. Have a good rest of your day.